Yeah, who said that? Gravity. Yeah, gravity. Those are the four basic forces. And so here you might be thinking, well, Mr. Shane, if there's only four basic forces, strong nuclear, weak nuclear, electromagnetic, and gravitational, why are we learning all these weird forces, normal force, friction force, and tension? Well, we learn them because it makes it more convenient. It makes it easier for you guys to learn the physics. But I want you to know that on that basic level, friction force is just another electromagnetic force. Normal force is just another electromagnetic force, and tension ends up just being another electromagnetic force. They're all examples of electromagnetic forces at work, but we like to distinguish between them because it makes understanding physical things easier for you guys, for you little high school students. Okay, so that's friction. That's the definition of friction. Okay, friction. My goal is try to use the word friction in every sentence I use. Friction depends on two things. Because today is all about friction. One thing, and I'm going to be pretty quick with this, I'm not going to try to elicit responses from you guys. One thing friction depends on is the characteristics of the surfaces in contact. Characteristics of the surfaces in contact. Suppose, wearing the clothes I have, suppose I ran a little and then slid on my knees on this smooth tile floor. I'd be able to slide a pretty good way, especially if the floor was a little dusty. But what if I did this at home on my carpet? Would I be able to slide that far? No way, not on my carpet. I might get rug burns, but I wouldn't slide very far at all. Why? Because there's just more friction between the carpet and my jeans than between the smooth tile floor and my jeans. You see what I mean? I mean, one aspect of friction is just the characteristics of the surfaces in contact. Some surfaces have more friction with each other than other surfaces. Pure and simple. The second thing friction depends on is the amount of force with which the two objects are being pressed together. Amount of force with which the two objects are being pressed together. In the first Karate Kid movie, the one with Pat Morita and Ralph Macchio, not the more recent one with Will Smith's son, Jaden Smith, but the first one, because I've never seen the second one, but the first one, Miyagi, when he wants to make his hands hot and apply that heat to the kid's knee so that he will somehow magically be healed, Miyagi takes his palms, you remember that? And he doesn't just rub his hands together, no siree, he slams his palms together and presses really, really hard and then rubs his hands together, right? And are you guys okay with that? There's going to be more friction if my hands are pressed together than if my hands are not pressed together. It's easy for me to do this. It's hard for me to do that. You guys okay with that? That friction force depends on the force with which the two objects are being pressed together. Here, let me give you another example. Let me see. Gavin, would you mind standing up for a second so I can get your desk? So you're gonna have to stand there like an idiot.
All right.
Thank you. So here's Gavin's desk, okay? And the surfaces in contact are the bottom of the legs of the desk and the smooth tile floor. And so you can get a sense of how much friction there is by how much force I need to move this desk. And you'll notice it's not much force at all. Yeah, I'm able to move it pretty easily, except when it hits the tape. But I'm able to move it pretty easily. Oops, there goes your pencil. Wait. Here, I'm going to put it right in there. Alrighty, and another way you can get a sense of how much friction there is if I propel this table. And you notice it slid a reasonably good amount. Okay, now I'm going to change things without changing the characteristics of the surfaces in contact. Gavin, do me a favor, please sit in that desk. I haven't changed the surfaces in contact. Is it going to be easier or harder or the same for me to push Gavin around? Harder, right? Because I've changed the amount of force with which the two objects are being pressed together. Now the bottom of the legs of the desk are really being pressed hard against the floor. So I try to push Gavin. You see, it's very hard to push him. Not because I changed the surfaces of contact, but because I changed the normal force. In fact, if I try to slide Gavin, Chris, would you like to help me? Let's see how far Gavin slides. 1, 2, 3. Well, actually, he went pretty good, but I think it might be because we exerted so much force. Okay, thanks a lot, Gavin. Give Gavin and Chris a hand. They're good sports. Yeah. So I hope I'm proving to you that friction force depends on these two things. So because of these facts, I'm going to be able to get a nice, swell little formula that that tells me what friction force actually is. But before I do that, I want to talk about the direction of the friction force. Direction of friction force. Okay. So far, we've learned about two forces. Gravity. The direction of gravitational force is always towards the center of mass of whatever it is that's attracting you. That's gravity. So here on planet Earth, the direction of gravitational force is straight down to the center of the Earth. We learned about normal force, where normal force, when two objects are pressed together, the direction of the force is perpendicular to the surfaces in contact. Well, what if there's friction? What's the direction of the friction force? Like I've got this ring stand here, and I want to move it. And so in order to move it, in order to slide it, I have to exert a force this way. Well, what's the direction of the friction force opposing me? So what's the relationship between the direction of the friction force and the surfaces in contact? Yeah, are you guys thinking in the same direction or parallel? Yeah, so that's how friction force is different from, let's say, normal force. When I have two objects pressed together, normal force is perpendicular to the surfaces in contact, but friction force is going to be parallel to the surfaces in contact. And so that's something you should know. Direction of friction force parallel to the surfaces in contact. And one more thing I want to point out. The amount of force with which two objects are being pressed together. Hey, we've got a name for that force, right? What do we call the force with which two objects are being pressed together? What's that force called? We learned it yesterday?
No.
Yeah, normal force, right? That's normal force. So I want you to be aware that friction force depends on the normal force between the two objects in contact. Okay, great. So it's time to get an equation for friction force. Equation for friction. First of all, we need a symbol to symbolize friction force. We've already learned about normal force, which we call F sub n, and we've learned about weight, which we tend to call mg, depending on what the g is. Do you need me to provide focus?
There we go.
Great. I know, stupid camera. Thank you, though. So, well, now we need a name for friction force, and then we're going to call friction force by a lowercase f. Some books call friction force big F with a subscript of lowercase f, but we don't do that here, no siree. We call lowercase f. Here comes the equation. Friction force, which is equal to a lowercase f, is equal to a quantity that describes how much friction two surfaces have with each other, and that quantity is called the coefficient of friction. And then multiplied by the amount of force with which two objects are being pressed together, but that's the normal force. We have a special Greek letter for the coefficient of friction. It's the same Greek letter that we use as a prefix for SI units for micro, like micrograms or microseconds, and it's the Greek letter mu. So it ends up being friction force equals mu times F sub n, where mu is like the sound a cow makes, but with a Y in it. Mu times F sub n. Well, if only friction were that simple, I would just give you problems, you'd use the formula, then we'd be done and we'd be all happy. But friction isn't that easy, because it turns out there's actually two types of friction. And let me demonstrate that to you in a second. Let me get a drink of water first. There is two types of friction. Let me get this over here. Tell me, anyone who's had experience pushing a big, heavy, let's say, couch across the floor, or had to move a refrigerator across the kitchen floor, tell me, is it harder to start something moving or to keep something moving? How many people say it's harder to start something moving? Okay, good. So we all have that experience, because it's true. And that's because there's two different types of friction. There's the friction that keeps something from moving. That is the friction that happens between the two objects when they're both at rest relative to each other. And there's a type of friction that you get when two things are in motion relative to each other. Let me show you that now. I'm going to exert force, okay? I'm going to exert force to make this thing start moving. And you're going to see this needle move, and it's going to be theoretically, maybe 10 or 12 newtons. I mean, there's going to be some large amount. And then once I start it moving, you're going to see that needle drop. Let me show you. Here we go. Did you see that? How the needle got pretty high, but I'm making it go pretty high. I can make it go as high as I want by just really jamming on it. So I'm trying not to cheat too much, but I'm trying to let you see that it does, see there, it didn't take much to get it moving. See, my problem is this board is so irregular that it's hard for me to get consistent data. But I just want you to see, for the most part, it usually takes more force to get something moving than to keep it moving. For me, approximately 10 newtons to start it moving, approximately 8 or 9 newtons to keep it moving. You guys okay with that? So because there's two different types of friction, we have to have two different formulas for the two different types of friction. Before we start talking about those two different formulas, I want to convince you that there is actually two types of friction. Static friction, which you get when two things are at rest relative to each other, and kinetic friction, where two things are moving. Okay? Remember this thing here? Why is it that I can get more friction when they're at rest relative to each other than when they're moving relative to each other? Why do I get more friction when these two surfaces are at rest rather than when they're moving relative to each other? Yes, Gavin?
I'm just going to get a shot at it, but I'm assuming maybe it's because their bonds are together at first, so you need to break those bonds, and once they're broken, it takes less energy to keep them broken.
Okay, cool, beautiful. You guys okay with that? If they're at rest, we've got all these bonds. That's correct. But there's another issue too. Think about how these bonds are formed. Why is it that I form more of these bonds when they're at rest relative to each other than when they're moving relative to each other? Because I form more of these dipole-dipole intermolecular bonds when they're at rest. Why? What's the difference between the two objects being at rest relative to each other versus being in motion relative to each other? Like when they're at rest, remember these bonds form just randomly, they form just things are, electrons are randomly scooting around, and then suddenly you find yourself randomly having a dipole, and then you get your bond. So what do you get more of here? I guess I won't try to squeeze it out of, but what advantage do the things being at rest have versus them being in motion? What's that?
They have more machines at forming because they'll be at rest, so they'll have more time.
Thank you, Jonathan. Thank you. Thank you very much. That's totally correct. They'll have more time. When they're at rest relative to each other, they have more time. Given a certain amount of time, you have a certain probability of forming that intermolecular bond. Well, the more time you have, the more of those bonds you're going to form. Yeah, you got more time. That's it. That's why. So you get more bonds forming in the static situation versus the kinetic situation. Yeah, beautiful. Yeah, I was going to say something else, but I'm not going to. That's good enough. Okay, so we've got two types of friction. There's static friction, which occurs when the two surfaces are at rest relative to each other. Occurs when two surfaces are at rest relative to each other. And then the second one is kinetic, which occurs when the two surfaces are in motion relative to each other. Surfaces are in motion relative to each other. This idea of static friction, one thing that happens when, in real life, sometimes you get a situation where you have a bolt that's holding something in, and then there's a nut on the bolt, and the nut is tightened really, really tight so that the nut and the head of the bolt are exerting a tremendous amount of force on some metal plate in between them. Well, if that sits there long enough, what's going to happen is the molecules, so many molecules on the head of the bolt will end up bonding to the metal thing that the bolt is attached to, that you end up getting what's called a cold weld. And sometimes the nut will be on, I don't know why people, last period people were laughing about talking about bolt and nut. Is that funny? Is that like a euphemism for something? Okay. But anyway, so the bolt and the nut and the head of the bolt are in contact for so long that they end up getting welded together, and it's called a cold weld, where you didn't, impose heat on it, you didn't do anything to force them, you didn't solder them together or glue them together. Just the fact that they're in contact with each other so long and form so many of these bonds that after a while they just get welded together. They're one piece now. They're not two separate pieces of metal. They're one piece of metal. Yeah, cold weld. So you can't expect, when you bolt things together really tight with metal, you can't expect that bolt to last forever and for you to be able to unscrew it. Eventually they cold weld together, So anyway, let's go ahead and investigate these two types of friction, and we're going to do static today. We're not going to get to kinetic, so there's no homework. I just want to let you know there's no homework tonight. I apologize for not giving you homework, but there you go. No homework. Let's talk about static friction. Okay. Yes. Sure. You gotta go, you gotta go. Here we go. I am trying to move this guy. I am exerting 2 newtons of force on this ring stand. 2 newtons of force. There we go. Tell me, how much friction force is opposing my 2 newtons of applied force? Yeah, 2 newtons, right? Because the net force on this guy is 0 because it's not moving. The acceleration is 0, so the net force is 0. So it's 2 newtons. Okay, now I'm going to exert 4 newtons of force. Tell me, now that I'm exerting 4 newtons of force on this ring stand, how much friction force is the ring stand exerting to oppose me? 4 newtons, right? So do you see, unlike, other forces like weight, I mean, I weigh 260 and that's what I weigh 260. There's no changing that. But I want you to see that the friction force changes. It depends. It depends how much force I'm exerting. Let me ask you this. What's the static friction force on this ring stand now? What's that? Yeah, 0? Okay, sounds like you said cero. Like Spanish, like Espanol. Cero, yeah. 0, right? So, but with static friction force, there is a maximum amount. What if I exert too much what if I exert too much force here? More force than, just 1 second. Someone's calling me. Hello? No, this is, no I don't. Jordan Hernandez?
I brought you chili.
Which teacher are you trying to call?
And I brought cookies. Chocolate chip cookies. You're too good. Are you happy?
That's not me. No problem. Bye-bye. I should have raised you for interrupting my lesson. Okay, so you guys okay? There is a maximum amount of static friction force. If I exert too much force, what's that thing going to do? Start moving, and then I'm in kinetic friction land. I no longer have static friction force. So you see, there's going to be a point, yeah, I can exert 4 or even 6, but pretty soon I exert enough force that the thing starts moving, and it's not static friction anymore. So our formula for static friction ends up being as follows. Static friction force. It's still going to follow that equation, but I'm going to call it F sub S to tell the world, hey, this is static friction force. And it's going to be mu sub S, F sub n, where mu sub S equals the coefficient of static friction, which gets its own number, separate and distinct from the coefficient of kinetic friction. But there's one more thing. Is the static friction force always equal to this? No, it can be less. It can be as small as 0. So I have to actually write this. I have to say it's less than or equal to mu sub S F sub n. That mu sub S F sub n is the maximum static friction force. So another way of writing this equation is to go F sub S max equals mu sub S F sub n. And I just want to make it really clear that that maximum static friction force, F sub S max, equals the maximum static friction force that can be exerted. So another way to put it is the maximum force you can exert on something before it starts moving. Maximum force you can exert before the object starts moving. Because that's the maximum static friction force you're going to get. If you exert more force than that, then the object's going to start moving on you. It's time for us to do a couple of problems together, and then we'll be done and we'll complete our little lesson on Monday. Here's our first example. Example number 1. I have a 200 Newton weight, and I'm going to push on that 200 Newton weight. And it turns out that the coefficient of static friction between this box and the floor is equal to 0.7, or let's call it 0.70. That's the coefficient of static friction between the box and the floor. How much force must I exert to start that box moving? How much force must I exert to start the box moving? Well, do we have a process? Have I taught you some process or procedure that you should use when dealing with any sorts of problems involving forces? Yes, thank you very much, easier. Free body diagram, right? And so that's what we're going to do. We're going to start with a free body diagram, and then we'll do sum of the forces equals ma, just like we do with every problem. Sure, I've learned a new force, but that hasn't changed anything. We're still going to be using the free body diagram. So let's look at the situation. I'm pushing on the box, friction's opposing me. Name me one force on this 200 Newton box. Yeah, good, the weight. So you got 200 Newtons down. What's another force acting on the box?
Normal.
Yeah, normal force. The floor is pushing up. And I know most of you can just look at that and say, oh, normal force is equal to 200, but I'd like you to go through the process, because soon I'll be giving you problems much more complicated where normal force isn't going to be equal to the weight of the object. What's another force acting?
You.
Good, me. I'll just call it F. The force I'm exerting is F. And what's the last force?
Friction.
Sure, friction force. And I'm going to call it F sub S because it's the static friction that's opposing me. I'll define up as positive and to the right as positive. Now, I'm going to do sum of the forces in the y direction equals MAY. I'm going to do that because I need to know normal force in order to plug into this formula and find friction force. So let's do sum of the forces in the y direction equals MAY. I got normal force up. I got my 200 Newton weight down, and I got mass times acceleration. What's the acceleration in the y direction? Is it accelerating upward towards the stars? No, is it accelerating downward towards the center of the earth, where the devil lives? No. So it's equal to 0. So I got normal force equals 200 Newtons. You guys okay with that?
Bless you.
Okay, well, now let's go ahead and turn our attention to the x direction. Sum of the forces in the x direction equals max. I got two forces in the x direction, F, which is positive, and static friction force, which is negative. F minus static friction force equals m times. And here's something that I must tell you. You had no way of actually knowing this. What's the acceleration of this object in the x direction when I'm exerting enough force just to break the bonds, to get it going? Well, I'll tell you, 0. We assume if I'm exerting just enough force to break the bonds, I'm not exerting enough force to get it moving. So you get this weird situation where I've broken the bonds, but it's not moving yet. So the acceleration would be 0. Let me just tell you right now, I want to make sure it's clear to you guys, because there's going to be a lot of people that with the static friction situation, they're going to go, well, what's the acceleration? And the answer is going to be, for the most part, in this sort of situation, 0. Friction. Acceleration equals 0. You exert enough force to break the bonds, but the box doesn't move yet. You've exerted just enough force to break the bonds, but the box isn't moving yet. You're not exerting enough force to move the box. So this guy ends up being 0. And then last thing, F sub S is equal to mu sub S F sub N. So go F minus mu sub S F sub N equals 0. And now I can substitute in mu sub S, which is 0.70. I gave it at the beginning of the problem. And F sub N, which is 200 newtons. And so I need a force of 140 newtons. Any question or problem on that before we do another one? Yes?
So that 140 is that's how much you need for the box to start moving.
Yes,
So-
for the box to just start moving.
So before you put the maximum force you could exert before an object starts moving. So I guess to me it would sound a little bit confusing because I thought you would have to go like over that in order to start moving.
Right, you would. You'd have to go a smidge over it,
Okay.
like 140.0001.
Okay.
Yeah, so that's like our borderline force. Okay, there's one more example I want to give you, but we only have 1 minute left, and that's not enough time to do the example. So I'll just save it for Monday. And like I said, you have no homework tonight, and then Monday we'll complete our discussion about friction, and it will be good. And thank you very much. Thanks.